This is part 2 of lecture 11 on ultra-wideband technology. In first part of this lecture, I talked about incentives and pros and cons for using ultra-wideband technology. In the second part, I will start talking about channel modeling, application to ultra-wideband, and then about ultra-wideband systems. For channel modeling, basically, we have like two models. We need two models. Model for path loss, which gives us the coverage, and models for multipath. If you remember, for path loss models, in indoor areas, which are the areas that ultra-wideband technology is used, we had like this partitioned, distance partitioned models. The same models are also used for ultra-wideband. Then, for measurement systems, again, similar measurement systems that we had. The only thing which is changing is like antennas. And for multipath models, the general multipath models are very similar, but since it is ultra-wideband, the paths are not anymore radial. So in particular, I talk about all of these implications in a very short few slides. The first thing is that for measurement system, this is the network analyzer measurement system that we have seen in chapter 4 and in lecture 4. Now, however, in there I had omnidirectional antennas. We were just like quarter wave, like mass antennas. But in here, they have variety of antennas. One is the so-called bow tie antennas, like this. The other popular one is like cone antennas, like this one. This is a cone with a hat. These are two popular type of antennas for ultra-wideband. Now, then you put them on the network analyzer, and then you have the transmitter and the receiver. Receiver signal comes back, and network analyzer calculates the channel impulse response and frequency response. First frequency response, then channel impulse response. So this is the same measurement, same frequency domain measurement system that we had before, except that now the antenna has changed. These antennas are very small, the size of a dime. Okay. This one is bigger, a little bit, just like a couple of inches in each direction. Now, the first thing is, okay, if I do that type of thing, what type of channel measurement I get? This is the type of measurement. This is the frequency response of the channel. And this is the time domain response of the channel. The bandwidth that I'm covering in here is between 3 to 6 gigahertz. So the width of these pulses is 1/3, like 0.3 nanosecond. Very, very narrow pulses. But except that, I mean, if you remember in chapter 4, we were talking about wideband measurement systems, which had bandwidths like 200 megahertz. This one has a bandwidth which is 1 order of magnitude more than that. So what will happen is basically we have the same stuff, but now rather than having one pulse in 5 nanoseconds, we have like in 5 nanoseconds, you're going to have like 10 pulses, something around that. So I have more pulses. These pulses are more and more. As I increase the bandwidth, these pulses combine, and I will have another version of this thing. Okay? Again, I have examples of that somewhere, I think. Where is the example? Not in here. In the next lecture, I have examples of that. But anyways, so this is basically what it is. There is no difference with the past, except that antenna has changed. Now, so I can calculate the received signal strength the same way that you did on your project number, I believe, 2 or whatever. 2 or 3, I think project number 2 was the one that you did the result of measurement, and you calculated distance power gradient. Okay? You can use the same stuff with the result of measurement in here and try to fit it. So these are a bunch of received signal strengths from the multipath profiles, very similar to what you had in your project number 2. Now, you can fit, in project number 2, you fitted one line like this to that. If you fit one line, the distance power gradient is 3.3. These measurements are done in Atwater-Kent laboratories. But we see this pattern that at the beginning they are like this, and then the shape, I have a faster decay. Up to 10 meter, I can fit a line. After 10 meter, I can fit another line. Then distance power gradient in the first is like 2.7. In the second one is 6.7. This is called partition. And we did partition type of thing before as well. And we remember that one of the early partition models was the one by Ericsson. And then some of the early measurements was the ones that Ganesh did actually in here in like 1989 or something like that, which he took a building and partitioned the building. This is very similar thing. And actually it's very fashionable because we saw the same pattern also in 802.11 channel models. So for all the indoor environment, people try to do partition modeling. And up to a certain point, they take it like one area, the second one, the second area. Really, these two areas are differentiated by line of sight, obstructed line of sight, in a sense. Because up to the place that I hit the walls, I'm like a free space. And my distance power gradient is like 2, around 2. And after that, it starts to decay rapidly. So this is what I have in here. And 802.11, ultra-wideband, and 802.15, all of them, they do the same thing. For ultra-wideband, the first person who did this type of measurement and modeling was a group of Professor Schultz, and in particular, Mo Win, who is now professor at MIT. This is a typical model that one of, I believe, my student developed here for one of our projects. Jin Rang Lee did that. And basically, path loss is like if you take this thing, just only one of them, one line, the path loss model would be like this. 42 is the path. I have 3 gigahertz to 6 gigahertz. The center for that is 4.5. If you put it in the equations for calculation of path loss in 1 meter, you get 42 dB. And then this is 33 log 10 of the associated to this line. Or if you want to have 2 lines, this is 2.7 associated to this part, and this is 6.7 associated to this line. So this is 1 line and path loss, 2 partition and 1 partition. And this gets partitioned at 10 meters. Okay, so here we are. Just a review of what we had in the past. The only difference for the path loss in here is this path loss in the first meter. And the second one is that after the break, this guy dies very fast. This is like 6.7. It's a very high gradient. You remember that for, like, if you get Alexander's work, which was the first indoor calculation of ALF in early 1980s, which we discussed in, I believe, lecture 4, 6 distance power gradient was associated to buildings with a lot of metal. If we do one single line fit. So here, after 10 meters, building is really killing the signal very rapidly. Up to 10 meters, it's okay. I mean, you can modify this model, make it up to a wall 2, and after wall, it could be something like 5 or something like that ends up. But anyways, these are like engineering solutions. There are a variety of solutions. And this is one that Jinrang picked up based on this pattern. Because you see up to 10 meter, and you see that after 10 meters they go down really. Okay. Now, so that's about path loss. So there's nothing special about the path loss, except that path loss in first meter is stronger, and also it decays very rapidly after the first break. The second thing is like multipath model. Multipath model, the ones that we were using, for example, for 802.11, and before that, we were using the ones for, like, let's say GSM, cellular, or PCS, which is JTC model. You remember them. For GSM and for the JTC, the path loss, the time domain model was like several taps, like 4 taps, 6 taps, spreaded in time. And you did some simulation of JTC, for example, in what? In your project tree. Okay? Then, however, those models assume that I have like 4 to 6 paths. And now look at this. This is too many paths, really. Okay? When the bandwidth is like bandwidth of like GSM 200 kilohertz, or PCS applications like 1 megabit per second or something, I don't have as many paths. For these paths, the model which fits better, or people have resorted to, is back to Sol-Valenzuela's model, SV model. You remember that Sol-Valenzuela model was something like this. I have a bunch of clusters. Okay? And within the clusters, I have these rays. And this model actually is not recent. It was published in 1987. But even, nobody was using that. Up to what? Up to late 1990s. But anyways, when they came to, the first people who used a little bit of this type of thing were people in 802.11. And then, followed by that, the ultra-wideband people, 802.15 people, tried to use that. Basically, in this model, I have the so-called like clusters, 1 cluster, 2 cluster, 3 cluster, and I have rays within the clusters. Arrival of the rays within the cluster is Poisson. Arrival of the clusters themselves is another Poisson. And the rate of arrival of these 2 Poissons are different from one another. And then the paths within the clusters, they are decaying at different rates. Okay. Now, and these are equations which are relating the path strengths to the distance and to the decay rate. These two. Now, if I come now, so in here, if I want to just look at that intuitively, now I have 3 clusters in here and paths rays within each cluster. Now, statistics of each of these paths in Sol-Valenzuela model is Rayleigh. They assume all of these paths are Rayleigh fading. Now, when I come back in here, I see a sort of clusters. This is like a sort of cluster. This is another cluster. This is another cluster. This is another cluster. I see clusters, really. It's not a bad idea. That's a good model, clustering, for this type of application. When bandwidth becomes very high, I see a sort of pattern of clusters. But, for example, for bandwidth of 200 megahertz, measurements of Ganesh in his thesis around 1989 showed that, we didn't see any clusters, really. We couldn't find any cluster. But measurements that Sol-Valenzuela did, also the bandwidth was around, I think, 100 megahertz. I was very surprised at how they find the clusters. But when you go to like much wider bandwidths, like this, I see some pattern of clusters in there. So that's a good model. So it starts to revive. Okay, so that's one point, one difference. So the cluster or Sol-Valenzuela's idea is coming back to model. The second issue is that now if I take the strength of the paths in a particular location, in Sol-Valenzuela, that value is Rayleigh. But when we were in chapter 5, I told you that measurement of Ganesh actually, first time in here, showed that it is not correct. It's log normal distribution because the bandwidth is so high. But that conclusion was in the back burner and nobody was paying any attention until 802.15.3 actually came back and they looked at that literature and that model. And what they did, they modified the Solers model in two directions. One is in the arrival of the paths. The other one is in the strength of the path. In the strength of the path, they did the same thing that Ganesh was talking about. They put log normal distribution for that. And for the arrival, they tried to look into variety of options. One of them is delta K or modified Poisson. Now, finally, they came up with this model that if you look at these paths that you have in here, a strength of these paths are given with these equations. The distribution is log normal. Phase is not uniform anymore. It's either 0 or 180 degrees. And then these are equations to calculate that. And these are the decay rates. These are the equations for calculation of mean and variance of this log normal distribution. I mean, detail of that is not that important. The only point is that they are specified by 802.15.3a. But a specification, the key is that the paths are log normal. Phase is not uniform. It's just binary. If you use that for simulation, you get something like this, as compared with something like this. But remember that in here, it's only magnitude. If I get only magnitude of this, all of these negative things become positive. And they will look similar to this. Okay. So basically, in terms of modeling of the channel, if you want to say 802.15.3 model, basically is the same as those wideband models that we had studied earlier. For each path, the amplitude is no more Rayleigh, it's log normal. And the phase, they assume it's either 0 or 180 degrees. Because you have isolated all the paths, so the relative phase between them, they assume is not important. I think it's not a good assumption, actually, to my opinion, because if you want to take this ultra-wideband model and then use it also for other bandwidths, it's not good anymore, or it may be damaged. Okay, but if it is used only for ultra-wideband, it's good. Okay, so that's one thing. So that's about the modeling. So we see that the modeling efforts still continues for understanding. The next issue is the issue of system. For the systems for ultra-wideband, they have a variety of modulation techniques. Impulse radio was the traditional one, but this one is the one that existed before this wave of wireless information networks. Because impulse radio, as we talked about earlier, was a phenomenon of 1950s. And wireless information networks started in 1980s. But for the impulse radio, the required bandwidth was not granted by FCC. With the bands and that FCC released, see, this is what FCC released. But what for impulse radio people wanted was the shifted version of that to the beginning. So you start from here and come to there. As soon as it was not successful, people took this band and they treated either with a spread spectrum, which was success of cellular, or with OFDM, which is the success of wireless LANs. I mean, survival of wireless LAN industry. Okay. Now, we start with impulse radio now. So, there are three technologies, traditional impulse radio, and then these two survivals of cellular and wireless LANs. And let's see that what are these technologies, very, very briefly. Impulse radio, basically, you have a pulse like any other pulse. This is like a raised cosine pulse. And you want to send it. If I have like if I don't have ultra wideband, means that W over FC is a very small number. I can design a good antenna, and I receive almost the same pulse at the receiver. But when I have ultra wideband, I cannot design. Frequency response of the antenna comes to the picture and actually changes the shape of the pulse. Okay? This particular example, I have a bow tie antenna. It's patented bow tie antenna by Time Domain, a company in California. The received signal is something like this, which is a sort of derivative of this guy. See, whenever this one is flat, it's 0. Then when it's moving fast, it goes up. Then in here, it comes up. So this is really derivative of this pulse. Okay? But anyway, this is still a pulse. Okay? But the shape is like this, rather than to be like this. And that's how they do the ultra-wideband communication, the original, which is the impulse radio. Now, the next step is that, okay, what is the spectrum of this pulse? So this is my received pulse, something like this, which may have an equation like this, can be represented by an equation like this. This is one of those. If I assume it's of this form, I take the Fourier transform of this thing, and if I sketch it, I have something like this, which comes from 0 up to 5 gigahertz. If you take 3 dB from the top, this bandwidth from here to here is between 1 to 3 gigahertz, like 2 gigahertz band. Okay? This pulse, the width of the pulse is something like from here to here is like 0.2 nanosecond. It's a very, very, very small value. Okay? So what they do, they take this very narrow pulse, which is fraction of a nanosecond, which occupies a bandwidth which is like several gigahertz, and then they want to do communication. I told you originally they were using that for radar. Now, if you want to do it for communication, what you have to do, number one, is that you have to repeat this thing somehow, and change the polarity and repeat it or whatever. Huh? Now, first let's see what is the effect of repetition. If I repeat this pulse, for example, every 100 nanosecond, like the way that this is in here, what will happen is that in the spectrum I will have things like this. And the distance between these two is what? Is 1 over this distance in time. So basically I have the same pattern of a spectrum, but I have fluctuations ups and down in there. This is like time domain, frequency domain, and when I repeat the pulse. This is just basic idea that you want to get, some basic intuition. That now if I repeat the pulse, my bandwidth stays the same. Bandwidth doesn't change. But ripples on the bandwidth go a little bit up and down. Okay? Now, FCC comes with what? With some masks, like this. This is the FCC mask, for example. This is the FCC mask. If you design now a signal, your spectrum should fit. So, should fit in here, for example. But original impulse radio was fitting in here, between 0 and 5. Okay? Now you have to modify the filters. The filters originally were difficult anyways. Now they get even more difficult. But people are doing that, and there are some solutions, in fact, around, and people are still continuing in that area. Now, the next issue is that, okay, these are my pulses. I can repeat them. This is the spectrum. And if I can fit the FCC, what is my communication? The original communication technique in here was actually suggested by Movin and Schultz, and the company called Time Domain, all of them in California. And the technique that they use is the so-called time hopping spread spectrum. To understand time hopping, I have these narrow pulses which are coming out of the BOA antennas between transmitter and receiver. I take the time and I divide it in TFs. TF is like 100 nanosecond. Every 100 nanosecond, I send a pulse. Every 100 nanosecond, I send a pulse. And I repeat this pulse over and over. Okay? So I repeat them n-s time. Then, in each of these time interval, TFs, I take the time, I divide it in TCs, which I call them chip periods. Then, to know that which of the chips in here I'm using, similar to like frequency hopping spread spectrum, I select one of the NH possibilities in here. In this case, NH is equal to 3. Okay? So I put my pulse in the third slot of time. Do you remember in frequency hopping, I had a random number and I put my frequency in that random. The frequency is 3, then it's 5, then it goes 4, then it goes 6, etc. In here, the time slots. I have NS time slots, okay, and I jump in time in there. So that's why they call it time hopping. How do you generate the PN sequence in there, the random number, the same way that I was doing for frequency hopping spread spectrum? I create the random number generator, and so that's why they call it time hopping spread spectrum. What is the advantage of this thing, and how does it compare? Advantage of this thing is that if rather than this, for example, I was using direct sequence spread spectrum, then I had this bit in here, and to transmit this bit, I would multiply it with these chips, and the chips are either plus minus 1, and I would transmit them. So always I was transmitting in time, I was transmitting some signal. But look at this. In here, in each chip, rather than sending a full pulse, in each chip, I only send a narrow pulse. So transmitted power in here is much less than transmitted power in here, because I'm doing pulse transmission. Pulse transmission is the most effective way for power efficient communication. The first people who used pulse type of transmission are people who were designing remote controls using infrared. They want this remote control carry the battery over several years, so they do pulse transmission. Okay? After that, people came to, one of the first people to practically looking into this problem were the people involved in Bodyland, the ones that I have seen. Okay? People in Bodyland, they wanted to design, they were the first people who wanted to design like a transceiver, like a wristwatch. So they wanted to have very low power, so they resorted to pulse transmission. And that brought the idea of ultra-wideband, at least from one end, to applications, and related it to application. Now, okay, so in this part, I'm taking advantage that in time domain, I'm sending pulses rather than chips, so I save in the energy. But again, in the world, you never gain without lose. What is the loss? The loss is that in a spread spectrum, my spectrum is inverse of this length, which is something like that. In here, that's inverse of this, which is like fractions of that. So I inverse it is several times more than that. So ultra wideband is if you want to look at that, ultra wideband is spreading a spread spectrum even further. Because in each chip of a spread spectrum, I'm sending now a narrow pulse rather than the thing. So that's why they call it ultra wideband. So if you want to call it, is a spread spectrum signal. That's the way that we see it in here. So if in here my bandwidth was 1 over TB, in here is 1 over TC, in here is 1 over TP, which is duration of this pulse. Okay? But anyways, it's interesting. It's a spread spectrum. It's interesting from 2 points of view. Point of view number 1 is that this is low power transmission. Point of view number 2 is that power spectral density becomes even smaller. And this is very good for interception, for military application. You remember that one of the advantages of direct sequence spread spectrum was that in this type of communication, your power spectral density is low, comes around the noise. So nobody realizes that you are communicating. While if you have like frequency hopping spread spectrum, people can put a scope and see that, yes, you are communicating. So that's the advantage of it. This one is even better than that. Okay, for interception. Now, this is a typical receiver for time hopping systems, and this is a typical communication thing. What they do is that for communication, they take one of these periods T sub f's. See, if I have one T sub f, inside T sub f, I want to send a pulse. In order to send a pulse, I have divided this T sub f to chips, similar to like direct sequence chips. Okay, so I have these TCs, and I want to send a pulse in there. So what I do, randomly, I select one of these chips using a random number generator. If I know that I'm sending in here, now this pulse that I want to send, okay, I will modulate the location of this pulse. Means that if it was 0, for example, I leave it to stay here, and if it was 1, I will delay it a little bit. Delay it equivalent to delta. Okay? So, in a sense, it's also pulse position modulation for differentiating between zeros and ones. Okay? So, I want to send a chip. What do? Okay, I find the number of the chip, I come to that time slot, and in that time slot now, if in that particular chip I was sending an information bit, which was 1, I put 1 delay, and if it was information 0, I put another delay. Now at the receiver, if I cross-correlate these two, if I multiply them to one another, if they are in the same location, I integrate them, they add up. If they are a little bit apart, when I multiply them, one of them is 0. So they average out. You see how I detect them? So at the receiver, then I create two sets of pulses. One, the ones with delay, and one with no delay. And I multiply these two receive signal with these two replicas. Whenever they are on the same thing, they add. So I compare them to one another, and I say whether it was 0 or it was 1. And this is actually basically the same receiver. Okay. This receiver is coming from a paper in here. Papers by Movin and Schultz. All of the material that I gave you in the past few slides is coming from these two papers. And this is how I will detect it. These are just equations for that. But the basic concept is that I multiply it with the replica and I integrate over the time. And these are some like performance curves for a variety of parameters which was generated by moving. And that much of detail we don't want to go to. Okay? But basically we know then how they did the impulse radio, okay? How they create the transmitter, how they create the receiver, and it is possible to calculate their performance, and these are the result of the performance. And the only difficulty that they had was what? Fitting to the bandwidths of FCC. Now, the advantage was low power, very low power. Okay? So this is impulse radio technology. How about the other two technologies? One is direct sequence ultra-wideband. The other one is multi-carrier OFDM. Direct sequence ultra-wideband people, they take this band, which is between 3 to 10 gigahertz. They create two bands inside that. One band is between 3 to 5. The other one is between 6 to 10. And then they generate pulses inside here or inside here, like this pulse or like this pulse, and they use these pulses for communication. Now, okay, I have 2 gigahertz in here, and I have like 4 gigahertz in here, bandwidth. The chip rate that I can run in here is something like around 1 giga chip per second. In here is around 2 gigachip per second of pulses like this. Now, number one, why they neglected this 5 to 6 gigahertz in here? They don't put anything in 5 to 6. They shade that because this is the place that 802.11a is running. Number two is that I have two bands. Why two bands? Well, center frequency in here is 4, center frequency in here is like 8. Okay? We remember that if I increase the center frequency, my coverage becomes worse. So if I come to here, I have shorter distance coverage, but I can go to higher data rate. If I come in here, I have longer distance coverage, and I can come to lower data rate. So that's like a good solution, very flexible. And what they do is that they actually take these pulses and they do a spread spectrum with that, direct sequence spread spectrum with those pulses, like in-phase, quadrature phase. But this is baseband modulation, really. It's not RF modulation. Means that I'm not modulating it over anything. I just send the pulses. Now, then they use, how do they use this thing? What is the, in fact, medium access control? The medium access control, they call it FDM, CDM, TDM. What is that? FDM is frequency division multiplexing. I have two channels, this one and this one. Okay, so I have an area like that. I use channel A in here, lower band in here, lower band in here, higher band, lower band. These three are lower band, these three are higher band, these three are lower band. Do you follow? This is like inside the building. These are rooms inside the building. I put 3 lower bands, and between I have higher band. To control what? To control the interference. Then, within each of these bands, they are dividing the system with different codes, different direct sequence codes. So I have channel A, channel B, channel C inside that. That's where this CDM comes in. So first was FDM, second was CDM. The third one is that now inside this area, I have like multiple users. How do I assign the multiple users? They are separated by time division multiplexing. Did you follow? So I have frequency division multiplexing with lower and higher bands. I have code division multiplexing by using different codes for direct sequence spreading. And I have time division multiplexing by differentiating different users. Okay? So this is one example of implement. Then, a standard specifies more details. They give you codes for this. These are the code that they use are 2 box, 4 box, and 8 box. Okay? These codes are ternary codes, which are either 1, -1, or 0. This type of ternary codes are not used in radio communication when you do the modulation. They are used, for example, in similar things are used to, ternary codes are used in gigabit Ethernet, for example. Okay, when there is no modulation. Because when you have modulation, then, in between you have difficulties when you have nothing. You don't send anything. But when you have baseband, you send 1, you don't send anything, then you send -1. That's no problem. And as I said, it's applied in Ethernet, gigabit Ethernet, fast Ethernet, and also now they are using that ternary codes for ultra-wideband application. Now, if they want to change the data rate, these are some performance in there, and these are some performances. If they want to change the data rate, these are the performance of these codes. Now, they come to things like this. They send a pulse, and then send the next pulse, next pulse, next pulse, next pulse, next pulse, next pulse, when they are hopping. Here I have a very high data rate. Okay? Now, if I want to reduce my data rate, I send a pulse, I wait, I send it in the next one. The data rate in here is half of the data rate in there. So there are details of that nature which are going to, which are main details of the standardization. However, the basic concept for direct sequence is the one that is given in here and in here. I have 2 channels. I have these pulses, and I'm sending the pulses in time using direct sequence spread spectrum. And that's basic concept. That's enough of basic concept. Okay? Okay. Now, another competitor of this technology is the so-called multiband OFDM. Multiband OFDM. Before I go there, remember that in here I had 2 channels. One of them was 2 megahertz band. The other one was 2 gigahertz. The other one was 4 gigahertz. Okay? In the direct sequence ultra-wideband technology, I have 2 channels. One is 2 and one is 4 gigahertz. We call this low band, we call this high band. Now in multi-carrier OFDM or multi-band OFDM solution, they have so many channels. 3, 3, 3, 3, 2, which is 14 channels. Each of these channels are 512 megahertz bandwidth, which is less than half of the lower band of direct sequence. But in here I have more flexibility. I have a bunch of bands. What they do is that in each of these bands, they are using OFDM signal. But in the OFDM signal, when I have 3 bands, they do the so-called time frequency hubbing or time frequency jumping. Means that I send one symbol here, then in here, then in here, and then I come back to the first one. Okay? So I have, while I'm changing the time, I'm also changing the frequency. Nothing that new, really. It's similar to the stuff that we were doing earlier. Maybe, if you want, in frequency hopping spread spectrum, we do similar type of thing. This is not very strange in that sense. But in frequency hopping spread spectrum, we were jumping randomly among a lot of carriers. In here, I have only 3 carriers or like more that I'm jumping in. I can combine 2 of them. I can combine all of them. Up to 14 of them I can combine. And then jump between them. How about each time that I jump, what do? I send one OFDM symbol. And that's it. That's the technology which is called multiband OFDM. Okay? So the pulses are OFDM. The channels are like up to half a gigahertz. The other one, channels are 1 and, if you want, 2 and 4. And pulses are just direct sequence spread spectrum. Just directly they go out. There's no OFDM in there. So that's the basic difference between these two technologies. This is a typical like OFDM modulator that the standard body recommends, which is similar to what others that we have seen before. And this is a sort of time frequency multiple access operation that you're jumping in time over different frequencies. So at this time you're in frequency 0, next time you're in frequency 5, next time you're in frequency 3, next time you're frequency 1, next time 6, next time 4, next time 2, etc. and you continue and go. Okay. And I think with that, I mean, these are more details about the type of codes that they are using. These are the frequency time coding. I have like 3 channels. Okay. The length of the code is 6. I jump like this. I mean, they have group bands up to 4. If you come in here, up to 4 time division codes. The 4 codes that I have, one of them is 1, 2, 3, 1, 2, 3. The other one is 1, 3, 2, 1, 3, 2. The other one is 1, 1, 2, 2, 3, 3. The other one is 1, 1, 3, 3, 2, 2. When I compare them, they always have some hits. They have like 2 hits at the same time. This one again with this one has 1 hit in here, 1 hit in here. But 2 hit out of the 6 slots. Okay? That's what they have in there. And these are the four of the bands. What are the 4 bands? 1, 2, 3, 4. For the last one, since I have only 2 codes, places I need 2 codes. The 2 codes are in here. 1 code and 2 code. And the slots are like 4 time slots. Either it's 1, 2, 1, 2, and nothing after that, or it's 1, 1, 2, 2. Again, I see that I have 2 hits between the 2 symbols. So more or less that's the type of code which are used for time frequency multiple access in multi-band OFDM systems. And these are a variety of data rates that you can support with this type of system. With the detail of the codes, etc. Data rates, it starts from 55 megabit per second, goes up to 480 megabit per second. These are some sort of range of coverage for these guys. It's more example, and I think if you want to compare now the 2 solutions, this solution provides more flexibility, multi-band OFDM, and then the other one, which is direct sequence ultra wideband, can provide higher data rates. can provide data rates up to gigabit per second because you have wider bandwidth. But whether people need really 1 gigabit for a user, because the applications that you are interested in is USB port, that's one of the highest data rates, which is like, 400 megabit per second, around 400, 450 megabit per second. You don't need more than that. But in here you have less flexibility and you're using higher frequencies all the time. But in here you have choices to stay in lower frequencies all the time. Now, keep in your mind this bandwidth of 500 megahertz and like 2 or 3 gigahertz. We will see, I will show you in the next lecture that actually these are better for positioning than the other ones. Because when you make your band too much wide, then you make more errors actually in time of arrival estimation because the paths become so weak. But we don't want to go through that now, and we do that in the next lecture, which is lecture 2. So, in summary, in this second part of lecture 11, I talked about 82.15 channel model, 15.3 channel model for ultra-wideband communication. And briefly, I went over 3 system implementation for ultra-wideband. One was 1-band impulse radio. One was 2-band direct sequence ultra-wideband. And the other one was like 14-band multiband. That's why they call it multiband OFDM techniques. And I told you about the medium access control that they are using. Medium access control in impulse radio was like time hopping technique. And then for the second one, which was like the 2-band system, direct sequence, it was a combination of time division multiplexing, frequency division multiplexing, code division multiplexing. And then for the multiband OFDM, medium access control was the so-called time, frequency, multiple access, if you want to call it. Means that I have like 3 bands. I jump between the 3 bands in different slots of time. In terms of physical layer, the difference between them was that in impulse radio, physical layer was just direct pulse transmission. And in the second one was direct sequence spread spectrum. In the third one, it was OFDM. With that, I can close this second part of lecture 11 if you don't have any questions.